Hello and welcome back. Up until now, we have done the beam analysis in using the beam element and 2D plane stress elements and shell elements. Now we want to go into the 3D elements, the solid element, and for this one, we will first try using just the beam and then apply boundary conditions, and then we will create a 3D model using the two pins, and finally we're going to use the shell mesh for 3D analysis. And by the way, this is the correct shell mesh, and the one we did yesterday in the past video was not correct one, because you cannot have a planar shell mesh. Shell mesh is always extruded. So I did it the same model using the extrusion, and we have the same dimensions, and the element size is 0.1, and we again have these two as fixed supports, and then displacement is 3 mil. So we get some results like stress is too high, but it's at a localized region. And if I want to see that, it's not like I should be expecting at the beam, but I still see something like a neutral axis and like high stress region and low stress region, but the peak stress is completely confusing and misleading. Now this is due to the boundary, because the displacement is at an edge and it's not distributed like it should be. But let's see the force reaction what it is, and the force reaction is 37.5 pound force, which is completely incorrect, and this is wrong. This is wrong results. Let's see what do we have it in Ansys, or sorry, Abaqus. So in Abaqus, this was the results. Now the stress, again we see the same thing as we see in Ansys. The stresses are localized, very high stresses, and these orange ridges, they have something like 1525 or something, but the force reaction here is completely accurate. It's 16.72, whereas it should be 16.28. So the force reaction is in some agreement, but the stress is not. So let's just try the same thing with using the solid model, putting the pins below it, and so we have the load and then 11th. So I tried this model using the same problem, creating the frictional contact between these two and these two and these two, but it didn't work out. It would always say that displacement increment for contact is too big. But I did have success using the shell mesh and results. So the shell mesh, it gave me good answers, 1596, which is like acceptable, and we can refine it using more refined mesh. But the force reaction is completely crazy. Like RF is 1.865, which does not make sense. And this can be the reason, or this can allude to the conclusion that we are now solving a frictional problem rather than a beam problem. And likewise, we can do it look in Ansys. This is the model. This is the model with the shell mesh. And again, we can see that deformation is somewhat, I had to pause it because it was taking too long. The stress looks fine, and the force reaction is completely crazy. I mean, I had to stop it. And another thing is that for the solid elements, we can still see that now we have a bad boundary or a wrong boundary, and maybe we just keep meshing and then we can have our results. But it seems like we have pretty refined mesh using zero point 0.1 inch as the sizing, but with with the solid elements we get different problems than we get at the beam problems, with the beam elements, or we can have the 2D elements. Now this is now we have to be very careful when we are defining our problem. So the entire scenarios that we discussed, the entire conclusion is that if you do not know what to solve or how to solve it, you probably gonna end up having results like these. And if you do not understand your boundary, you're gonna end up having wrong results. Now we want to analyze the software capability for both Abaqus and Ansys, and let's see if we have the same problem. So using the shell mesh and having almost the same elements, 68,000 and 69,000 are nodes. So I have like 67,000 nodes, and the Abaqus was able to finish it in like 13 minutes. But it was really hard for Ansys to converge, and it just could not converge in like 12 minutes and 34 seconds, and I still don't have like a whole lot of results. So for shell mesh, for this case, I would say that Abaqus made it. But let's see the other one, like the 3D elements. So we need to look at the mesh in problem, and there we have the mesh is 300,000 elements, 366,000 and 366. Now we need to check it if we do have the same mesh. So 300,000 and 366 and 366, we have the same mesh here, and it took Ansys 1 minute and 13 seconds, or let's see how much time it shows here. So CP time is 322 and elapsed time is 73, or total CPU time for main thread is 63.6. Now let's check it for Abaqus as well. For Abaqus, total CPU time is 93.4, whereas in Ansys it's how much it was, 63. Now if you're just looking for something that which one should you use or which one should I use, now you should be wrong, because unless I know what I'm computing, these comparisons don't mean anything, and maybe either of these have stability issue or something else, or I have modeled the wrong thing. So the idea here is to show that how you can set up the same input and then get the same output. Do you get it? And if you don't, then what's the reason for it? Like, which element are we looking at? Which boundary conditions are we looking at? So these elements, these numbers, and these seconds, it would mean nothing if we don't know what we are solving and why it's giving you so much time. I hope that clears out the advantage and disadvantage thing, and have a very good day. Take care and bye bye.